Hello, everyone. Welcome to the Cornell University Autonomous Underwater Vehicle Team High-Level Vehicle Design and Risk Management webinar. Let's wait 1 second just to make sure that sound is working properly, and then we will continue. All right, everything is looking good, so we will get right on with it. I apologize for the lateness of this webinar. I had a conference come up last week, but better late than never. All right, so what is this webinar going to go over? So in short, we're going to go over determining system requirements. We're going to do basically a system breakdown and a subsystem division based on those requirements. Scheduling based on these requirements. So it all comes down to basically working your way down from your system requirements, which I will help you determine. Risk assessment is a big portion of this, so I'm going to go very much into depth on this. I think it's something that RoboSub teams tend to neglect for some reason, but you'll see why it's important. So as for the rest of our webinars, we will have a Q&A session at the end. Not expecting too many questions, but if you do have a question, send it my way and it'll get answered. You can send all questions to leader@CUAUV.org. All right, sorry about that. I was hearing myself. All right, so determining system requirements. First step to doing so is grouping the tasks. So most tasks can be grouped into very similar categories, and you can very much determine what you want to do based on this. If you plan for one task in one of these categories, you have the hardware to attempt them all. You might need to add some hardware to this, but in essence, you have the basic system that you need to expand upon. Now, in order to determine which one of these categories you want to do, you're going to want to look at your skill set and your resources. Look at points earned versus effort spent ratio. So a lot of basically the tasks at RoboSub are very difficult. They give you a lot of points, but sometimes it's just not worth it. For instance, the torpedo task for the 2014 competition was very difficult to attempt because of the green color versus the green background at Transdeck. Most teams just decided, it's very difficult to do. We're not going to be able to, make a tuna vision system to tag green on green, and the points are just not worth it. So most teams did not attempt it. I don't think it was attempted even once. So take this as a lesson. You don't have to do everything. Just do what is optimal and what you can do effectively. All right, so these mission element categories, quote unquote, um, basically here's how we break down the obstacles. So first off, you need navigation. You need your sub to move. I think that's a basic requirement for RoboSub. Every team should aim to have the most effective navigation that they can. So forward vision tasks are one of these categories. So buoys fit very nicely in forward vision. All you need is navigation and forward vision to attempt buoys. Add to that maneuvering. You need slightly better navigation, but it's still just a forward vision task. Now, to expand on forward vision, there are a couple actuator tasks. So you have the torpedo task and the forward manipulation task. So these are things that you could do once you have forward vision. Now, I want to emphasize that these forward vision tasks are enough to qualify you for finals. They are, more than 2,500 points, which has been the cutoff for finals in recent years. So if you just focus on forward vision, you can do these. These are all fairly well stringed together, maybe except for forward manipulation. But even without that, you can qualify for finals. So just this one category is one area of focus. Another one would be downward vision. So for this, you just need, navigation once again, but also a downward camera system. So what does this net you? It nets you the ability to follow paths. So paths are very important. They can get you to tasks such as the bins. Bins by themselves, you can't just do them with just a camera. So you will need an actuator system to do them. There's also the downward manipulation task, so the sorting task. This can technically be done with just downward vision. So this category, even without downward manipulation, is enough to qualify for finals. So this is very good as a starting point, or a field of focus. I just want to focus on downward vision. That's perfectly fine. It can get you to finals, and then you can expand to other things. Now, this is what most new teams seem to go for nowadays. So, start with navigation, but then they realize, pinger is a very easy way to get, 2,500 points. So they go straight for the pinger. They just make a hydrophone system. I wouldn't be surprised if, there are subs without cameras that just have hydrophones on. Now, let's discuss why that's not such a great idea. So choosing what to attempt, let's just start with that. Picking one capability that is within your realm of knowledge. So if you're confident in signal processing, if you're confident in your electrical skills, go for hydrophones. Like that's perfectly fine. If you're confident in your mechie skills and your vision skills, you can do downward vision or forward vision. Just remember this will involve some sort of actuators and a lot of vision processing. But, if you just pick forward vision, you're perfectly fine for your first or second year. You will make it to finals if you spend time perfecting it. Now, you want to expand on the knowledge gained for the following years. So say you do forward vision and you accomplish maybe buoys, maneuvering, your first year, you want to expand to maybe torpedoes your following year, and maybe forward manipulation the year after that. So what if you finish perfecting a system early? Say, you chose forward vision as, your task. That's great. Make sure it's working 100% of the time. This is not just a competition about accomplishing the task. It's about accomplishing them consistently. That's why there's only one final run. It's there to show that your sub can do things every single time perfectly. So, once again, I'm going to use forward vision as an example. If, your original goal was just to do maybe buoys and maneuverability, and you got those working 100% of the time, go ahead and attempt torpedoes. Try to add on a system to do those. Now, you don't want to harm the reliability of your other tasks in doing so. So make sure that no matter what, you don't lose reliability on the things you've already perfected. So implementing just hydrophones, as I mentioned, is usually a bad idea. It makes it hard to expand into vision. Most of the tasks at RoboSub are vision tasks. So starting with hydrophones and not focusing at all on cameras generally leaves you at a dead end. However, if you do start with vision, you can tackle many more tasks, and hydrophones can be considered a parallel addition. So, I have easy addition here in quotes. It's not easy, but you can add it on as a parallel system. It won't affect your cameras. It won't affect any of that. So attempting a few tasks and doing very well at them is better than attempting everything and failing. So pick 2 tasks that you're really good at, that you want to perfect, that you can do, that can get you to finals, and just do that. Do it right. Get it right 100% of the time. So as an example, I have McGill. They were a new team last year. Their goal was just, attempt the first few tasks, gain some experience, and go from there. So they did that very well. Their reach goal, however, was to do hydrophones. They had, a strung together hydrophone system, but they ended up almost dead reckoning an octagon, which is very impressive. They almost made it to finals. So they had their vision tasks very well pinned down, and then they decided to go for a reach goal. This is very commendable. This is something that indicates, skill. It indicates that, they're making the right decisions. So let's look at subsystem features. So basically, each addition that you add to your sub, each set of tasks adds complexity to your vehicle. So you have your basic navigation. So this is what you need in order to do anything, honestly. So for navigation, you need your thrusters, you need sensors, you need a waterproof enclosure, you need a frame, maybe. You can probably get around that. You need some sort of batteries or power system. And you need, a controller that takes what you tell the sub to do and, makes your thrusters do it. Now, I want to emphasize you don't actually need, 6 or 8 thrusters at the beginning. 4 is just fine. Now, depending on where you go, you're going to add different things. So you can take the route of forward vision, downward vision, or hydrophones. These will all mean, adding different things. Forward vision will entail adding a forward camera, maybe, implementing some sort of vision processing, all the electronics behind, getting your camera to work. And you'll probably need a slightly better computer in order to do vision processing than you would just running a controller. For downward vision, obviously you need a downward camera, you need vision processing as well, and a better processor, and all the hardware that comes along with it. For hydrophones, you're going to need some sort of elements. These are generally pretty costly. They're an investment, and you're going to need some sort of signal processing, which is often the difficult portion of this task. So that's a very large investment of time. Now, based on what you do, you're going to want to expand. So it's not a bad idea to expand in a parallel direction, but I would recommend focusing on one of these columns. So if you go for forward vision, you should be going for, the forward vision actuation systems. So I just did forward vision, I just did buoys, great, I just did maneuverability, I'm going to move on to torpedoes and forward manipulation. So what does this add to my system? Well, this adds, a pneumatic system. It adds a torpedo firing system. It adds electrical controls for this. If you're doing forward manipulation, it usually involves some sort of sealing for, a rotary shaft. So you're going to have some sort of motor, some sort of dynamic sealing. You're going to need to get those skills. So, when you're adding this, keep in mind what it what it adds to your system, what type of complexity. Now let's look at downward vision really quick. Downward vision for the actuation task, it's bins. So you're going to want some sort of pneumatic, some sort of solenoids, electrical controls. You're going to want to be able to make droppers. So this adds, a slight level of complexity. However, if you look at it, these two systems work very well together. They both require pneumatics, just in slightly different ways. They both require very similar electrical controls. This requires dynamic sealing if you're going for forward manipulation. But if you decide to do, torpedoes and bins, then you just need pneumatics. So, look at clumping tasks together based on, requirements for your system. So maybe you're going to choose to go forward and downward cameras, be a little daring, and then go for torpedoes and bins, your following year. The hydrophones route leads to a very, very difficult task in recent years. The sorting or, object recovery task has been very, very difficult. It does require downward vision and hydrophones, so it's unlike your other expansion categories. So sorting does require pneumatics. It does require, electrical control system for this. It might require dynamic sealing. It's also very, very time consuming in order to practice. Very, very time consuming in order to tune vision. This is something that you leave, for your third or fourth year at least. I would definitely focus on this ahead of time. All right, so let's look a little bit into risk management. So risk management is the identification, assessment, and prioritization of tasks and risks. Sorry about that. So it's an important field of engineering, though it's often neglected at RoboSub. You see teams taking very, very ridiculous risks for not much benefit. Consistency is key to RoboSub. Consistency and high risk do not mesh well. If you take a lot of small risks, you will get very good consistency, and you'll do well at RoboSub. So why is risk management important? Let's just look at an example. So assume you have 10 projects on your vehicle that all need to work in order to have a successful run. Now, each one of these projects has a 95% chance of success. So, some simple math, 10 things working in series at 95% success rate, that leads you to about a 60% success rate overall. That's not exactly good. If you're only getting, 60% of your runs working, chances are, Murphy's Law, everything is going to go wrong, especially right when you need it, right during semifinals, right during your final run. So you want to keep risk very low, very, very low. You want 100% chance of success, if possible, on as many things as possible. You want, some risk only in very specific areas, very easily fixable areas. Risk stacks very quickly, especially in a system with many components, leading to very low success rates. So in a system like an AUV, you have hundreds, if not thousands, of subsystems, each with failure points. So stacking those together, it's a miracle that these subs even work sometimes. So how do you identify these, chances of success? Like, how do you identify a risky project versus a safe project? So a risky project or decision is defined as one that has a high chance of failure. So just look at, your skill set, look at the project. Do you have your doubts about it? Like how do you feel about it? Like, if you're attempting something like custom thrusters and it's such a complex project, no one has ever done anything like it before. Maybe you've attempted something like it in the past and failed. That's very, very high risk. Be very careful with that. Hydrophones the first time, that's very, very high risk. It's a huge gamble. You know, you maybe have 3 or 4 iterations on your boards before, you know, putting them into action. It's very, very high risk. It takes a long time to develop. Complex circuits are very high risk just because they require so much more debugging, so much more skill to do. Complex, large sealing systems, you know, dynamic seals, also very, very hard to do. So safe options might be something like, you know, instead of custom thrusters, you just buy off-the-shelf thrusters. You know, those pretty much come with a guarantee of working. Hydrophones. For hydrophones, you know, it's very hard to get, you know, a high chance of success. But okay. But instead of relying on it, why don't you, you know, turn it into a less risky project by putting it on research and development for a few years and, you know, not relying on it. It's difficult to explain how to determine if a project is risky, but it's definitely possible. This is really up to you and determining what your skill set allows for. So to summarize this, determining how risky a decision is, many factors are involved. So for instance, have you done anything similar with success? If you're looking to do custom thrusters, have you done dynamic sealing before? You know, if you're looking to make a custom PCB backplane, have you done, you know, board-to-board connections via board before? You know, how many iterations can you go through for this project given your time? You know, do you have time to sit there and make, you know, 10 different copies of this board before, you know, maybe getting it right? The more time you do give yourself for a risk, the better it will turn out. Now, the important thing is if other systems rely on this, you know, risky system working, then it might be, you know, escalating your overall risk. You know, if you're doing something sketchy with your batteries and your whole system relies on batteries, obviously, this is probably not going to end up well because your whole system cannot run without this, you know, low chance of success system. So let's look a bit at risk mitigation and prioritization. So progress demands that risks are taken. I'm not going to deny that. If you want to, you know, get better at something, you're going to have to slowly take risks. For us, 2 to 3 large risks a year tend to be manageable. So this is generally our rule of thumb. We take 2 or 3 major large risks a year, and we try to dedicate as much time to them as possible. So a couple examples of this maybe would be implementing custom thrusters, switching to a double hole design that requires, you know, additional seals, additional machining, very precise machining. So it is a very large risk. A PCB backplane is also a very large risk because it doesn't really come with a backup. Now, we also tend to allow for a number of small risks, though enough small risks tend to compound to one large risk. So you have to kind of keep track of them. If you say yes to a lot of small things, eventually it becomes major. So examples of like small risks would be maybe consolidating 2 boards into one, so increasing complexity for the sake of decreasing size maybe. Something like vector thrust, which is easily removable, and you can just slap on thruster straight onto your vehicle instead of actuating it. Custom active acoustics. It's a risk because we're investing time into it. However, we can easily just say, we don't need it. We're going to take it off without much impact. A new camera, it means time spent. It means, a new enclosure for it. A new computer means debugging. All these little things, 2 days spent debugging a camera plus 2 days spent, debugging a computer, it all adds up. It all adds delay. It's, small risks do add up. So just remember, sometimes you just have to say no to certain decisions. Um, you know, if you're, doing your high level system design and you have these 4 or 5 awesome things you want to attempt, they're all super risky. You just have to realize that you can't do it all at once. Pick 2 or 3 things you want to do, you really want to do, you think are realistic, and then push the rest, maybe just say it to next year, and just expand on what you have. So with this comes backups. You want to have backups on your backups on your backups. You always want to know exactly what you're going to do if something fails. So if a decision or project has a chance of failing, it better have a backup. I think this should go without saying, but I often see teams, just relying on their main system and just trying to repair that. And they spend many days repairing a system when they can just fall to their backups. So maybe spending 2 days falling to a backup system is better than, spending 10 days debugging a project that will probably never work. This is especially critical at Transdeck, where decisions like this may determine, whether or not you'll make it into semis or finals. Look at it this way: if you choose to debug your system and it takes you 5 days, you're not going to make it into semifinals. If you choose to just fall back on your backup and it takes you 2 days to implement, that's great. You're going to make it into semis. Granted, you might not be at tip-top operating shape. So the key here is to plan ahead. Always have backups ready. Know exactly what you're going to do if anything fails. Have a specific criteria for when you're going to pull the plug. If it's been 5 days and we still haven't gotten our thrusters working, we're going to just go ahead and buy new thrusters. We're going to replace them with these backup thrusters that are slightly inferior in terms of thrust. Just be ready to do that. Just plan it out ahead of time. Don't hesitate. So I'll give you a couple examples of backups. This is actually from our team from last year. We had a very ambitious valve enclosure with a number of custom seals, and it ended up not doing so well. It leaked, but we could not tell where, as is often the problem. So it leaked just about weekly up until competition. So we often found ourselves having to spend time debugging it. Our reliability ended up being around 60% for our runs back home. We knew this wasn't acceptable. We kind of wanted to gauge the competition before that. That was our cutoff, quote unquote. We said, if by semifinals we don't have a more reliable system than our competitors, we're gonna, fall back. So our first fallback was our previous year's valve enclosure. However, because of the age on it, it had a reliability of about 70%. Valves would fail, it would flood every now and then. So, it wasn't the most ideal system. So during, RoboSub, we opted for the backup for our backup, which was switching to our original valve enclosure, and as is tradition, filling it up with oil to basically displace any water that would come in. This ended up increasing our reliability to about 90–95%. Now, initially, this would not have been a good idea, just because oil in your valve enclosure means that you're probably not going to maintenance it very often. So during our at-home pool test, where we have to maintenance, every few days, this would have been a very, very devastating thing to do. However, at Transdeck, where we only have to make it run for maybe 3 days, it's a great decision to make. So we knew that, the cutoff for this was Transdeck. So if we didn't have it working by semifinals, we knew this is what we had to do. And, we ended up doing it. we all just sat down and said, okay, time to go to plan B. And it was, it ended up working out. Now, another example of backups for projects. So custom thrusters is something, we're looking to implement. This is a very difficult project. It requires advanced sealing, many, many CNC parts, much time invested, and it all needs to, be machined to a very tight tolerance, and it all needs to work together. So how do you mitigate this risk? So we're opting to make one prototype, then test it, and then make another 2 and test them, and then make the rest, maybe 10 or 12 of them. So even there, we have backups for our system. So we only need 8 thrusters, but we're going to make 10 or 12 just so that we can swap them out easily and diagnose issues without affecting our runtime. So the backup for that is to have a mounting scheme ready for off-the-shelf solutions. So we're always ready to swap back to ZBotics. We're always ready to swap back to VideoRay if we need to. So when is this deadline? So if after the second test, so not this test, this ends up not working, we are going to switch to our off-the-shelf solution. We're not going to spend time debugging this when we could spend time doing something else. So this lines up with the start of major manufacturing. So at the point where we say we're going to move to our older system, our off-the-shelf solution, we still have time to make all the edits in our frame and everything. So how do you do this? You make sure that these projects are on the fast lane. So custom thrusters actually started designing almost, I would say, right after competition started. They were already in CAD. They're actually being machined right now. So this is very much on the fast track. We knew it was a risky project, so we're putting as many resources as we can on it and, trying to mitigate the risk. However, we still have backups for this. So this brings me a bit into scheduling. So what I don't show here is this accelerated track. So if something does have a high level of risk associated with it, you're going to want to put it on the fast track. Now, there is a balance between, doing something fast. Okay, so the issue becomes if you put something on the fast track, it tends to have more error associated with it. So you can't exactly rush a project, especially when it's already a high-risk project. What you do is you put more resources into it. So you place better people on it, you give them more time to do it, you design review them as often as they need it, you put all your machining resources on the task, and you decide that you're going to base your system around that. You implement everything knowing that decision is bound to happen at some point. So in standard scheduling, I just wanted to point out a couple of things here. So here's what our schedule generally looks like by subteam. So you have, your brainstorming, your high-level design, and then, we split up into our subteams. Our subteams then, do their thing. Our mechanical team CADs, they might make some prototype in parallel with CADing, move on to manufacturing. Our electrical design team might, do schematic, then PCB layout, maybe do some prototyping in parallel, and then move on to populating their boards. Our software team is always coding, so they're probably one of the least concerning of the subteams, but it's important to keep track of them. So key things to look at here. There's a point here where we do what's called integration. This is a major bottleneck in our system. So without integration, we cannot continue. All the subteams cannot continue any work. We cannot move on to testing until integration is complete. So what do we do in order to mitigate the risk of integration going bad? So what we do here is we try to leave as much time for integration as possible. generally 2 or 3 times the amount of time that we think that we will need for it. So integration realistically should take about a week. We spend a month on it just in case something goes wrong. In case we need to order parts, you have a 1-week delivery time. So you want to be ready to do that. Now, what's important here when you have a block like this with a lot of parallel tasks going is I kind of line them up here in a way that shows when things should be done at the same time. So CAD, prototyping, and schematic should kind of be happening around the same time. And then manufacturing and populating should also be happening around the same time. So all your subteams should slowly be progressing at the same rate as it would be. So when your mechanical team is in CAD, you're going to want to discuss with your electrical team and see, what are their needs for the system, and vice versa. The electrical team will want to know, what is the mechanical team planning on. So it's very important to move at a very similar rate and communicate amongst each other as you're doing it. And you want to basically coordinate a very good deadline right here. So we know that everyone's going to have everything to the left of this line finished by February 1st. So we can move straight to integration for all of February and then move to testing during March. This is, a known fact. This has been the one thing that has messed us up the most within recent years. So this is the highest risk portion of our schedule, and this is what we spend the most time on. So some tips and tricks: stay very flexible. Designs may need to be changed. So be in constant communication with other subteams. Make sure you progress at the same rate. No one gets ahead of each other. You always have time to discuss a decision. Someone doesn't just make the decision without letting the other subteam know. The more meetings you have, the better off you will be. If you know what everyone else is working on, what stage they're at, you'd know where you should be. Always be ready to fall back to plan B and have a set of conditions for this to happen. Plan B, is not a bad thing. This just shows proper planning. It's not, you didn't disappoint anyone. This was the plan. This is what happens. In engineering, there's always something that will go wrong. So I want to emphasize that a series of low-risk decisions over a series of years leads to more success than taking many high risks at once. It's much more difficult to debug a system where everything is going wrong than a system where only one thing is going wrong. It's very easy to pin down exactly what is going wrong in a system where everything else works perfectly. In a high-risk system, chances are 3 or 4 subsystems may be failing at the same time, and you don't know where your problems are originating. So before questions, I want to emphasize that we do have a couple more high-level talks uploaded already. So we have one for mechanical, one for electrical, and one for software. I highly recommend those if you want to look at a more technical side of things. We're also going to go very much in depth on a number of subsystems. So, keep an eye out for that in terms of webinars. If you do have a question, send it my way. My email is leader@CUAUV.org. I'm going to go get a glass of water and I'll answer any emails that might come my way in a few minutes. All right, it's been 2 minutes now. No questions. That's perfectly fine. I hope you all enjoyed this webinar. I highly recommend you check out all the others and all our upcoming webinars. They're going to be a blast. Thank you for tuning in, and have a good Sunday.